All right. So we can continue now. Let me remove this meeting time. Okay, now, so the last thing that we did was this the development of the optimal transform called as KLT, the Caronin-Loewe transform. And in 2x2 case, we found the solution. For larger autocorrelation sequences, of course, it needs a little bit more attention. But the thing that is interesting regarding the eigenvalues and the eigenvectors is the following. Here, I have shown you a similar image before, but the last image that we drew was this in 2x2 case. The eigenvectors and eigenvalues are quantitatively visible from this kind of a scatter plot. It can be three-dimensional, it can be four-dimensional. Of course, it's not possible to visualize the fourth dimension, but whatever. But in two-dimensional, it's like this. So if you have this kind of a scatter plot, that scatter plot will correspond to an induced ellipse like this. Okay. Okay, like it's like an ellipse shape. Now, the ellipse has a few properties. One of them is the major and the minor axis of this ellipse shape, and the major axis will correspond to one of the eigenvectors, and the minor axis will correspond to the other basis or the eigenvector. Which are indicated like these blue arrows here that you see. So the eigenvectors are the principal axes of this ellipse shape. Then the eigenvalues are also somehow related to these. For example, there is the thickness or the width of this ellipse, and there is this tallness or the height of this ellipse too. These magnitudes are related to the eigenvalues. So the short arrow is related to, for example, lambda 2, and the longer size is related to lambda 1. Lambda 1 is the larger eigenvalue, and it's telling you that there's a lot of variation along that direction. For the data cluster. It shows the direction of the eigenvector, and it also shows you the energy, the liveliness of the signal along that direction. Whereas lambda 2 is in the orthogonal direction, and the variation in that direction is related to lambda 2, which is the amount of error that you will make if you just eliminate the second axis completely and you just replace it with a single 45 degrees tilted line only. It will only represent one direction and the other direction will be gone. It's a compression then, okay, getting rid of one of the two components, and the amount of error will be related to lambda 2. Square error will be related to lambda 2. So in 3 dimensions, how can you visualize things? You can draw a scatter cloud then. That scatter plot will be in 3 dimensions, okay? And it will be like my hand, for example. And the first eigenvector will be along this direction of my hand, which shows the largest variation. And the second direction will be orthogonal to that, but still along the largest of the smaller eigenvalues, which will be along this direction. So the first direction is this. The second direction is this. Where is this third direction of the eigenvector? That will be the thickness direction of my hand, because that is the narrowest. So lambda 3, which is the thickness of my hand, will be lambda 3. The width of my hand will be lambda 2, and the height of my hand will be lambda 1. All right. So in 3-dimensional scatters, those three directions will be orthogonal to one another. In higher dimensions, of course, it will be more and more complicated, and you have to elaborate on these things. So this is how you can visualize this Carnot-Löwe transform. It's pointing to a direction which shows the largest variation. So a question that comes to mind is, what if this scatter ellipse is essentially circular? Well, actually, that means that you cannot compress. No matter where you rotate to, it will be impossible to achieve any further compression. It means that x1 and x2 are not correlated to one another. There is no cross correlation between x1 and x2. And then you can still rotate by 45 degrees, but it will give you the same efficiency. So you're not doing anything wrong. That's why in 2 by 2, there's no other rotation or no other transformation. We have only this one. Because it doesn't matter if it becomes a circle, then you are doomed. But anyway, this is how to make a visualization of the rotation, axis rotation in terms of Carnot-Löwe transform, trying to find the major principal axis and the second major axis and the third major axis iteratively, finally remaining you with the minor axis. Now, the next thing that I want to talk about is regarding the two-dimensional transforms. The two-dimensional transforms are technically achieved by one-dimensional application to the rows and the columns, which means they are essentially not genuinely two-dimensional, but separable, two-dimensional, but separable to one-dimensional transforms along rows and columns. And once you do that, things become easy. It will be like this. Suppose that you have an image in the form of a matrix. So we have these rows and we have these columns, right? Of course, more. Now we want to, if you want to process this row, we can indicate it with a red like this, if you wish. This row, how can you express the situation in the form of a transformation? A transform is like this. There's a T transform matrix times X. X is a column vector. But this is a row vector. And since it's a row vector, how can I process this row? I can process this row by altering their orders by taking the transpose, like it will be X transpose times T transpose. So from this to this is your transformation. Since it's in the form of a row, I have to multiply it from the right-hand side with the transpose of my transform matrix. I am going to call it T1 transpose. So this matrix needs to be multiplied from the right-hand side. This matrix is, by the way, no, I can't say U. I have to say maybe X. Okay. This X matrix is multiplied from the right-hand side with T1 transpose. T1 is the transform that applies to the rows then. Now, how about the columns? Let me use a different color. Let me use a blue color. This column. Then those columns are already in the form of X. So there is capital T times X. So when I multiply from the left-hand side with this column, things are available to us. So I will do it like from the left-hand side, I will multiply it with the transformation T2. T1 is processing along the rows, T2 is processing along the columns. But typically T1 is the same as T2. I mean, we apply the same transform. Most of the two-dimensional transforms are inherited from originally one-dimensionally designed transforms, like the discrete Fourier transform or the discrete cosine transform, which is a very famous transform for compression purposes. We will see that. Now, this operation of capital T. Let me put it in black now. Capital T times X times capital T transpose, like this, will give you the transform of Y. Now, but in our previous examples, we were also talking about basis signals. So what is a basis signal that we are talking about in this situation? Is this, are these basis signals the basis vectors corresponding to the inverse of T and T transpose? Actually, it's a little bit easier than that. It's easier to understand that than that. Instead of basis signals, now we will have basis images. It is just like the example that we saw. So I'm referring back to the same example over and over again. This example or this example. As you see, I'm representing my image in terms of basis images, or this one particularly, these basis images. This 1 over 2, 1, 1, 1, 1, 1 over 2, 1, 1, 1, 1, 1, minus 1, minus 1, etc. These basis images are, how did I obtain them? I told you before that I have obtained them deliberately. I know what I had in my mind. Now I will explain what or why I achieved these basis images, because the way to obtain the basis images is as follows. From T, we come up with U is equal to T inverse, which are the basis, which gives us the basis signals in the form of rows. Again, U1, U2, all the way up to UN. These are the basis vectors, or the basis signals. So what is the corresponding basis image for this two-dimensional transform then? How can I obtain it? The way to obtain it is simple. You take, since you are multiplying from the left-hand side with the transform and from the right-hand side with the transpose of the transform, it essentially corresponds to basis images of, for example, U11 basis image to be the outer product of U1 and U1. I do not remember the outer product notation, but it's maybe perhaps a cross, this kind of an outer product. The outer product will give you a 2 by 2 matrix, by the way. It's not an inner product. The inner product of U1 with U1 will give you a scalar. The outer product will give you a 2 by 2 matrix. So if you cross product U1 with itself, it will give you the first basis image. If you cross product U1 with U2, it will give you the second basis image. If you cross product the second with the first, it will give you U21, which is another basis image. It will be U2 cross product U1. They will be different. So in the example that I have shown you for the basis images, what I really used was, I used U to be, sorry, it's not the cross product, but it's this U I'm talking about, this U matrix consisting of U vectors. In other words, this thing is 1 over square root of 2, 1, 1, 1 minus 1, which is the 2 by 2 transform, as we all know already. All the others will still obey the same result. So I will take the cross product of this within a scale of 1 over square root of 2, of course, with itself. So what will it be? It will be the square of 1 over square root of 2, which will be 1 over 2. So from here, I will obtain U11 to be equal to 1 over 2, the cross product of 1, 1 with 1, 1. And that will be literally 1, 1, 1, 1. And U1, 2, the cross product of the first column with the second column will give you, and here I'm always confused because I'm not good at mathematics. The scale will still be square of 1 over square root of 2, which is 1 over 2 times the cross product of 1, 1 with 1 minus 1. And I really don't remember whether it gives me this, which makes a sign change in the rows, or a sign change in the columns. I don't really remember that one. I have to check with MATLAB all the time. But if one of them is U1, 2, what I know is that the other one is automatically U2, 1, which will give you 1 over 2, 1, 1, minus 1, minus 1. So this will be the transpose of the other, but I don't know which is which. I don't remember which is which. And finally, U2, 2 will correspond to the cross product of, 1 minus 1 with itself, 1 minus 1, which I know the result to be equal to 1 over 2, 1 minus 1 minus 1, 1. So these basis images that I gave in the example were not just arbitrarily chosen to be like this. They were inherited or derived from this famous transform, which is the transform in 2 by 2 case. That's why I have chosen it that way in the example. But these are too easy. These U's are too easy. What could be other basis image examples if you use other transforms and then you invert the transform to come up with U? You have a transform matrix, and then from that transform matrix you come up with a U, and from that U, for each column of that, you take the outer product with the other columns or itself to come up with these many basis images. For example, if you have an 8 by 8 discrete cosine transform, then it means you have 8 columns. By cross multiplying with each of them, you will have 8 times 8, 64 cross products. And that corresponds to 64 basis images. And right now, I want to show you an example of that by making a new share, which is here. Okay. Now, these are the basis images of an 8 by 8 discrete cosine transform. So the cosine transforms, discrete cosine transforms, first column seems to be the a DC value, the same value for all the cases. So the outer product with itself, just like the one that we did, is 1, 1, 1, 1. So it's flat. And so this is flat here. Let me maybe, no, not really. Yeah, let me expand it a little bit. So the first one here is just a flat thing. The other one going in the horizontal direction, as you see, is increasing in frequency. The horizontal frequency is half a cycle here, then 3/4 of a cycle here, then 1 full cycle here, etc. It increases, and all the way to the highest number of oscillations horizontally. Then vertically, it also increases in frequency, and the others that we see here are just cross products of these. For example, 1 horizontal and 1 vertical oscillation is happening here, and 2 horizontal and 1 vertical oscillation is happening here, etc., which makes this kind of a rendition to the right-hand side. And as you proceed all the way down, which shows the maximum vertical variation, and then proceed to the right-hand side for the horizontal oscillations too, it becomes like a checkerboard at the last stage. Now, interestingly, or not so interestingly, these basis images are very good for energy compaction of the new representation, because any 2x2 image is essentially a linear combination of these basis images, some from the first, some from the second, some from the third, etc. And finally, some from this one, the last one. So if it is like that, then do we agree that for good compression purposes, the coefficient of the last one here should be small, because I'm going to crop them, I'm going to chop it off. And these ones will also be small, whereas the coefficients of these first ones, particularly this one, are expected to be large. If they are large, and if the others, the high frequency ones, are small, I can get rid of the high frequency context. And with the low frequency, it will be an approximation, but it will be a lossy compression. The loss is that I'm losing the high frequency content, so some detail will be lost, but I can get some really good compression ratios by only coarsely or approximately rendering my 8x8 image. Okay. By the way, it will be a good exercise for us to take a look at the basis images. Now, I'm sure you are able to see a bunch of small images here, but I want to show you the discrete Fourier transform basis too, which is at the right-hand side of the slide. Unfortunately, it's not at the, it's a little bit wide, sorry about that, but the right top corner here shows you the discrete Fourier transform basis images. Look at the basis images of the discrete Fourier transform in 8x8 case. As you see, they are different. They are not the same as the discrete cosine transform basis images. There are still 64 of them, but the basis images are increasing in horizontal variations and vertical variations, and then decreasing back, because these are essentially complex valued basis images, but I'm only showing you the real part here, or the magnitude, sorry, not the real part, but the magnitude of it. No, as I can see from the caption, it's the real part and the imaginary part, but the magnitude will resemble the same. And towards the center of the set, you come up with the highest frequency. And after that, if you proceed downwards or to the right, it goes back to the low frequency, back to the low frequency. And the in-between frequency oscillations are not cross frequency oscillations, but they are directional frequency oscillations. Look at this, for example, this one. It is just 45 degrees rotated version of a wave shape. And look at this. This is not 45, but less, maybe 30 degrees. This is less rotated. And this one here, over here, is rotated just diagonally. So the basis images will be pretty much different in discrete Fourier transform. We will also see what discrete Fourier transform will correspond, because we have to cover the typical transforms. We have seen how to optimize them, but we cannot use optimization all the time. We cannot talk about statistics and design a transform for compression purposes for all signals, because that would be very inefficient. The receiver will not be aware of my transform, so I need to transfer my transform as well, which will be very inconvenient. Instead of that, we will have fixed transforms that are optimum for some measure already, and both the transmitter and the receiver are aware of that, so you don't need to transfer the transformation matrix. For KLT, the receiver must know the KLT for reconstruction. But for DFT, you can just say it's DFT, or if it is DCT, you can just say it's DCT. So the receiver will know it immediately, which is a good way of doing compression. So in compression, we will be using DFT, we will be using DCT and things like that. But I wanted to show you what happens to those things in the format of two-dimensional transformation. The outer products will give you images like these. The images will be, of course, a little bit different if you have, let me click to this one and let me see if I may come up with some other basis image sets. Unfortunately, I don't see any different basis image. And the question is why? Let me click on the images. Well, I'm sorry about that, but most of the time, of course, we come up with a discrete cosine transform basis image. I can see some other basis images. This one, for example. I'm not sure if you can see it clearly because it's too small. It's at the top right corner here. Okay. Now, as you see, these basis images are like nonsense, but they may correspond to some optimization, like KLT or something like that, which will give you, of course, a complete nonsense set of basis images like this one. They are not nonsense for that particular set of images. They may behave or perform well. For a general class of images, of course, they will not be very much useful. For those, we need to use like the discrete cosine transform, like these, or the Fourier transform, which will help us to proceed with the JPEG image compression technique, because over there we will be using the discrete cosine transform. But I will explain that after we briefly mention about the discrete cosine transform in a little bit more detail. So now let me go back to screen sharing from my tablet. Okay, so this is what we have in two-dimensional transformations. And I'm not sure if I need to proceed any further regarding these optimum transforms. We can also talk about the singular value decomposition, which is another way of looking at one single image's best transformation or image-wise best transformation. Carnot-Liouville transform is a one-dimensional transform. First of all, we have to be careful about that. So we are applying it to the rows and the columns, but you can literally construct the basis images in a more awkward way using singular value decomposition, which is an algebraic methodology that you may remember from linear algebra. But it doesn't make sense for compression purposes. You cannot really compress with singular value decomposition. You can either expand or come up with no efficiency, because singular value decomposition requires not only the singular values, but also the bases, horizontal and vertical bases, on all those things. So we don't use them, but instead we use some other typical transforms. So I will quickly, move to the typical transforms. And of course, the first typical transform is the discrete Fourier transform, DFT, which is actually the discrete time Fourier series coefficient transformation of periodic signals. So we have a length n sequence, for example, and then we make a periodic replica of that. Okay, infinite periodic extension. So it becomes periodic. It is periodic with capital N. So how many Fourier series coefficients does it have? It's a discrete time signal. It has capital N discrete time Fourier series coefficients, CKs. are DTFS coefficients. And these DTFS coefficients, capital N of them, will be equivalent to the DFT of our signal. Our signal is here, it is X. The expanded signal is, let's say, X tilde. So DTFS of this X tilde is equal to the DFT, discrete Fourier transform of X. It's not the discrete time Fourier transform. Be careful. Discrete time Fourier transform is a different thing. Discrete time Fourier transform gives you a Fourier transform which is continuous in frequency in terms of omega. And it is just 2 pi periodic in omega. DFT is not 2 pi periodic or anything, and it is discrete in frequency as well. And the relation between them is, this is the samples of discrete time Fourier transform. So you have the 2 pi periodic discrete time Fourier transform like this. This is 2 pi, this is 0, this is capital X of e to the j omega, which is the discrete time Fourier transform. You may remember from signal sense systems. So DFT at n points, depending on the number of elements in this vector, will be the samples of this. For example, if it is 2-point DFT, then the sample will be this one and the one at 0, which is this one. So we are sampling between 0 and 2 pi. If you have a 4-point FFT or DFT, sorry, I'm stuck with this term FFT because that's the method to evaluate discrete Fourier transform. It's the fast method of doing it. It means fast Fourier transform, but fast Fourier transform is discrete Fourier transform. Just the method is fast. It's the same thing. If there are 4 points, then these 4 points, which are like 0, 1, 2, and 3, will correspond to the samples. If there are 8 points, then we will have these 8 points. And I will continue with the 8-point example. Like this is 1, 2, 3, 4, 5, 6, and 7. So where is 2 pi? 2 pi is always excluded because 2 pi is equal to 0. So this sample at this point is the same as this sample at this point because everything is 2 pi periodic. So as you see, the more DFT samples you get, the better continuation or approximation that you have for the discrete time Fourier transform. So if I ask you to plot, or if anyone asks you to plot the discrete time Fourier transform, this x of e to the j omega, you should try to obtain DFT using FFT in MATLAB, for example, with as many points as possible. So 8 points is clearly not enough, as you see, but more and more points, DFT will give you a very good rendition of this discrete time Fourier transform. So this is what DFT is. But for us, we are more related to the compression performance of this transformation. And the compression performance is not bad. It's quite good, actually, if you are careful enough. The care that you must pay, the attention that you must pay is as follows. The discrete Fourier transform will definitely give you a complex vector. So your original signal is real, x vector. You take the discrete Fourier transform of it. At the same size, you get a complex vector. So you have expanded the data, which is very bad for coding or for compression purposes. It's complex value. Every complex value will have a real and an imaginary part. So it's twice the data that you're looking for. It is expanded. But only half of the data is enough for you to render the discrete Fourier transform, because it is conjugate symmetric. the right-hand side of this part and the left-hand side of this part are conjugate symmetrics of one another. They are complex. So this part is the complex conjugate of this part. So if I cut from the half, from the middle, the right-hand side can be reconstructed. I don't need them. I don't need to represent them. I can just cut, send it, and the receiver will get it. Just paste to the other side, to the right-hand side by conjugating the values. And yeah, that's the DFT. Now I can take the inverse DFT and reconstruct my signal. That's why it's not so bad. It is complex valued, which is bad, but half of it is enough for you. And if that half of it is still capable of further elimination of some of the samples from the right-hand side, for low-pass signals like this, for example, if these centers are large in value and these middle values, central values around the high frequency, this is 2 pi, so the center is pi, those pi values are irrelevant or there is no such content, you can get rid of them. Or if the energy is low, you can get rid of them. You will only keep these parts, which are the low pass parts of the signal. Then you get a good approximation. It will be blurred, of course, because it will correspond to low pass filtering. Yeah, but that's life. I mean, you're gaining some compression at the expense of losing some detail. So discrete Fourier transform is perfectly available, but there is a better way of doing it, and we will also see that. But before that, let me give you the transform matrix formula for the discrete Fourier transform. So discrete Fourier transform can be obtained by multiplying your vector with a matrix, and that matrix is essentially this 1 over square root of capital N. This is an orthonormal DFT. In MATLAB, for example, it doesn't do this way. It uses the Fourier transform of DFT without this 1 over square root of N. So it's not orthonormal, but it's orthogonal. It's not just normalized. So the normalization is not in the transform, but it's canceled out in the inverse transform. The inverse of this will be the conjugate of it, the one that I'm writing, but the inverse Fourier transform of MATLAB will have 1 over N. So that's a pity, but it's done for historic reasons. The same is valid for normal Fourier transform in continuous time in signals and system courses. We use 1 over 2 pi sometimes. Sometimes in the transform, sometimes in the inverse transform, but actually the correct one is using a 1 over square root of 2 pi, both symmetrically in the forward transform and the inverse transform. Only then it will be an orthonormal basis. But this one is not orthonormal. This one is orthonormal version that I'm writing you. E to the minus j 2 pi over capital N times k times n. So these are the values of each matrix entry at the position of k and n. Of course, both k and n are between 0 and capital N minus 1. So this is the matrix. You form the matrix with these values. You render them. Of course, there is a fast implementation. We don't really multiply the vector with this matrix, especially at large sizes. If it is 1000 by 1000, for example, there's a fast way of making an implementation, which is due to the fact that some of these terms are common in different locations of the matrix, which can be combined previously, or the data can be merged previously and then multiplied all together with one exponential, complex exponential. So grouping and applying the multiplication makes it a faster way of doing it. This is not a digital signal processing course, but in the digital signal processing courses, this algorithm is also explained in detail. So you can find what is fast Fourier transform and how it works. For us, the more important thing is its matrix form, this one. So we just apply it. Okay, but the second one, which is the discrete cosine transform, is a better way of eliminating the need for the symmetry. In the discrete Fourier transform, I said that half of the data output is unnecessary for us, so we can cut it, and then we can reconstruct it by just conjugating the left-hand side. In the discrete cosine transform, the situation is in the reverse way. We take the signal and we make it symmetric already. Because if you have a symmetric signal, its Fourier transform becomes real, if you may remember. If x of t is an even signal, its Fourier transform becomes real. So we deliberately construct an even signal and then take the Fourier transform of it, but its Fourier transform will be real. And that Fourier transform will be the discrete cosine transform. First, let me start by writing the matrix in the matrix form. The matrix is like this. It is alpha m times, instead of this complex exponential, I have a cosine. Pi 2i plus 1. This I is not the imaginary I, okay? It's just the index divided by 2 capital N. So you may ask, what is alpha? Alpha m. Alpha m is unfortunately, and I will explain why it's like that, conditional. The alpha 0 value is different. It is equal to 1 over capital N in square root. For all other alpha, alpha m is equal to 2 over capital N if m is greater than 0. So it is usually square root of 2 over capital N, or square root of 2 over square root of capital N. Why is that? Let me start by explaining it. Because when m is 0, alpha 0, as you see, alpha m is here. When m is 0, it makes alpha 0. When m is 0, this is 0. This m is here, is 0. So it makes cosine of 0. And cosine of 0 is 1. Which means that for different m's, ci comma m, for m is equal to 0, excuse me, for different I values, ci comma 0 are all ones, 1, 1, 1, 1, along the column, let's say. So the column is consisting of ones. And I want to normalize it. It must have unit norm. So what is the normalization factor of that? If I want to normalize, I have to divide it by the norm of this vector of consisting of ones. What's the norm of 1, 1, 1, 1, etc.? The norm is square root of capital N. Okay, 1 square plus 1 square plus 1 square plus all the way to the nth one, 1 square, which will give you capital N. And then you take the square root of it, which will give you square root of capital N. So square root of capital N is the norm, and I have to divide by that to make it unit norm. Orthonormal means orthogonal and unit norm. So I have to divide by the norm, which means alpha 0 is necessarily this. But how come the other alpha m's are like this? It comes from the following explanation. So please try to pay attention to this. Please try to listen carefully. When m is not equal to 0, here I have pi times like 2i over 2n. So it's like pi times I over n. Pi cosine of pi times I over capital N. For a variation of I, this will make, when m is equal to 1, for example, this will make one complete cosine cycle, one complete cycle of a sinusoid. And what is the norm of a sinusoid? Maybe from power electronics courses or something like that, you may remember that the power of a sinusoid within one period is a square over 2. A is the magnitude of the sinusoid. It's square over 2. So the square root of it will become a over square root of 2. If a is equal to 1, where it is essentially equal to 1, there is 1 times cosine. So the norm needs a further normalization. So norm is reduced by square root of 2. It's like the energy under this rectangular box is twice the energy under this sinusoid. So the norm is square root of 2 less than the norm of the norm of this is the norm of this divided by square root of 2. So the norm is square root of n divided by square root of 2. And when I divide by, oops, sorry, what's happening? Excuse me. If I divide by x divided by square root of n divided by square root of 2, it essentially means I'm multiplying by square root of 2 divided by square root of n times x. And you see that that's what it is. So whenever m is different than 0, it becomes a sinusoid and its norm is reduced by square root of 2. So the normalization factor is not divided by square root of capital N anymore, but it is divided by square root of n divided by 2, which gives you this. That's why this alpha m is separate in these two ways, just the normalization between these two. And of course the others, because the others will have higher frequency. And the norms of these are all the same. Okay, they are all divided by square root of 2. Okay, this is the discrete cosine transform. And this matrix has an amazing property of being able to, or being able to construct using KLT. There is a relation of this one with KLT. So it is indeed an optimal transform, but it is the optimal transform for autocorrelation in a particular way, Rx, in a particular way, which is like this. Sigma x squared is also always there, of course. The diagonal is 1, and it goes on. And the off diagonals are rho, 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 rho. So it is an autoregressive sequence of autoregressive 1 with a correlation coefficient of rho. So the second term here will be rho square, and then the rho cube, and it goes on like this, rho square, and it goes on like this. This is rho square, rho square, rho cube, and it goes on like this. So if your autocorrelation is like this, which means it is an autoregressive 1 sequence with a correlation coefficient of rho, and as rho approaches to 1, rho is between -1 and 1, but if it approaches to 1, then the Cardinal-Loewe transform, or the basis vectors of this autocorrelation, you stack them and then take the inverse of the matrix to find the transform, will approach to the discrete cosine transform, and that's an amazing property of the discrete cosine transform. The proofs or explanations can be found. It's rather, it requires elaboration a little bit. Maybe I can ask it as a take-home exam question to show that as rho approaches 1, the KLT approaches the discrete cosine transform, which is this one. Yeah, but knowing it for the time being is more important for us. And the way to make an implementation or its relation to the Fourier transform is the last thing that I want to show you within the last 5 minutes or something, which is like this. So if you have a signal, a discrete time signal, x, let's say, x of n, we can say on the n axis, like this. Suppose these 4 values are the thing, and you want to have the 4-point discrete cosine transform of it. If you take the 4 points DFT of it, it will correspond to, I will draw it again for the DFT case with red to see the difference. It will correspond to the discrete time Fourier series coefficients of the periodically extended version of it, you may remember. So it will be like this, right? But in DCT, we first make a periodic extension of this one, not a periodic extension, but a symmetric extension, because we want to have a symmetric signal so that its discrete Fourier transform will be real, like this. So I fold it and have this signal. And then I periodically replicate this one. Like this. Sorry for the mess. It goes on to the left and to the right. Now I have a different signal. I will call this new signal x tilde of n. Now this new signal x tilde of n is supposed to have, it's not, it unfortunately doesn't, because there is a discrepancy in the center. It's not really very symmetric because the symmetry is around, maybe I should draw it with this red. The symmetry is around this and this point, which does not correspond to an index. So it's not really real that it will give me, but the idea is to get some real valued discrete Fourier transform from this longer sequence of x tilde of n. So you take the DFT of this x tilde of n, which is expected to be real, but I do not have the formula in my notes for this. But it will be 2n points. So it's a longer DFT that I have, but it's real. Can you understand the compromise between the DFT of this one? 2n point real DFT is here, but if you take the DFT of this one, you will have n point DFT, but it will be complex. So which one would you choose? Well, it depends, of course, but the one that we will have in the discrete cosine transform will have further nice properties. It will be real 2n point, but half of this one furthermore will be redundant still. Because of the conjugate of the first half will be equal to the second half, and they are already real, so there is no conjugation necessary. The 2n point real DFT will be real and symmetric. So because of the symmetry, I can chop off half of them. So n point real will be here. In the DFT case, I will have n point complex, but half of that n point complex will be unnecessary. So I will have n oops, let's make it red. N over 2 point complex is enough for me. So now you have to compare these two, N over 2 point complex or N point real. Which would you choose? Again, it's up to you. Efficiency is the same, but mathematically speaking, mathematically speaking, they are the same. But algorithmically speaking, I think the endpoint real real transforms will be easier for you to handle, to write loops for matrix multiplications and doing evaluations instead of trying to multiply complex values like in complex exponentials. But after all, the efficiency is supposed to be the same, and their efficiencies are indeed the same. One of them has a period of, or in the cosine term, it has pi times I times m over capital N. I am just canceling these two terms. This plus one is necessary to avoid the singularity of the discrete cosine transform matrix. If you just say that instead of putting this plus one, if you don't put it, then it will be pi times I times m over capital N, but that would make a singular transform matrix, which is not invertible, so we don't use that. So, but it's essentially cosine of pi times I times m over capital N, whereas in the DFT here, it is 2 pi times k times n over capital N. So the period here is capital N for this sinusoid, but the period here is, if you put this 2 pi to the left-hand side, if you say 2 pi I m over 2n, then you see the period here is 2n. So the period behavior of these two are different. One of them has 2 pi periodicity, rendering all the way up to n. The other one is cropping to the half size and putting all those n samples into the first part only. So the period will be 2 times n, because n plus n is 2n is the period in discrete cosine transform, whereas it was n in DFT, which is the period in discrete Fourier transform. That's the difference that you can see. One of them is taking the first half of the discrete Fourier transform and putting all these n samples inside it. The other one is taking the n samples all the way from here to here, but they are complex. So which one will give you better compression efficiency? Obviously, discrete cosine transform is preferable both in terms of algorithmic computational efficiency or programming efficiency, and also it's slightly better in performance when you are technically applying it to some particular transformations, because as you see, it is, as I told you, it is essentially the Carnot and Loewe transform for such signals with autoregressive one behavior, with correlation coefficient approaching to 1. So very much correlated signals are very good. They are very good for prediction. We know it. We know it from the first exam. And they're also good for transformation too. And if they are very good correlation signals, then you can perfectly use the discrete cosine transform. And that's fundamentally why we are using the discrete cosine transform in compression of images, including JPEG. Because image pixels, if you closely inspect the pixels, if you zoom to an image a lot and see pixel by pixel, you see that neighboring pixels are very much related to one another. They don't abruptly change in natural images, at least. So in natural images, they use discrete cosine transform. But the autoregressive one behavior changes. Most of the images are not stationary. There is a sky and cloud here. There is a house here. There is a tree here. So sometimes it's autoregressive one with some certain correlation coefficient for this part, But for the other part, the correlation coefficient is different. So we don't really take the DCT of the whole image. And JPEG does not work that way. After I stop, next week we will continue with that discussion of JPEG. JPEG splits the image into smaller blocks of 8 by 8, within which you have a strong autoregressive one behavior of correlation. So you can apply DCT safely inside this 8 by 8 block, and then another DCT within another neighboring 8 by 8 block, etc. So we split the situation into smaller blocks so that the correlations will obey the autoregressive one characteristics as rho approaches to 1. Within the blocks, they work that way. But if you go far away, because of unstationarity, the statistics may change, and we don't want that. That's why we split our signal into smaller chunks. We do the same for speech and audio compression as well. We chop the signal to smaller blocks and then process for compression individually. All right, so this is what discrete cosine transform is. I want to show you the basis signals. I have shown you the basis images of discrete cosine transform before today, but I didn't show you the basis signals of discrete cosine transform. We will also see that. We will see a few more typical examples, and finally we will continue and wrap up the whole course with the coding efficiency of these transforms and how to quantize them, how to make bit allocations for the transformations. And that will be the end of it. After that, I will not have any further topic to discuss. And slowly, it's your time to make your presentations. In the final week, within the final weeks, you will have to make a preparation of your project, submit the report, and make a presentation. So now I am stopping the recording. If you have any questions related to the course, you can ask now. Or if it is about the presentations that I'm mentioning, if you have, you can ask after I stop the recording. So do you have any questions regarding these things? We will continue with these transforms anyway, so it's not finished yet. Okay, you don't, then I'm stopping the recording and you may ask other questions if you have any.